Is it recording right now? It says starting. Okay, it's recording right now, I think. Yep, it's recording. So how can I share with you? I think I need to download it and then share with you guys, right? Okay. Is there any question, guys, about the syllabus? About how we're gonna discuss the topics? Okay, no question. Let me pick this thing again. So I will do only 1 hour course time, which is between 1 and 2. And if I feel like we need to do more, I can do it because it's gonna be my office hours. If you want, you can come. If you want, if you don't want, you can just leave. It's up to you. But the official hours only just 1 hour. And then next 2 hours will be my office hours, which means that you can come see me. You can ask questions. Okay, guys. And the office hours is not need to be like face to face. We can just set a remote meeting as we do right now, like individually. Then you can ask questions. Okay, guys.
Hocam ofis günleriniz için ne söylediniz? Duyamadım.
For the office hours, there will be like on Wednesday, starting from 2 to 16, like 14 to 16. And you can come see me, like face to face. You can ask questions, or if you don't have a chance, or if you don't want, if you want, you can create a remote meeting, and then I can join, do the one-to-one session, and then you can ask your questions.
Tamam, teşekkür ederim.
Okay, guys. So the first unit from the book, it's all about this part, chapter 0. Okay, guys, introduction part. So I'm gonna follow the book. Nothing else. I'm gonna follow the book. And at the end of each chapter, there are questions. And I encourage you to do those questions, which is because like they are related and they just strengthen your understanding of the topic. Try to solve them, exercise some problems. Some of them might be hard, so you can look at the answer for them, but try to solve as many as you can, and then just try to find an answer for them, because like it should be, the answer might be on the internet. There is no doubt of it, right? If you need some kind of answer, for example, if you just Google this question, you can find all the answer for this question, which I think it should be for the same for all the questions. Okay, guys. So let's start. Is there a way I can make this thing bigger, but I don't lose the pen? Let me see. Okay, I have it. What if I make it full screen? It doesn't let me do the full screen mode. Why? Okay, I don't know why, but I hope that you can see what's going on there. Okay, guys. So this class is about basically what we can do with the computers. What we can do and what we cannot do with the modern computers. So this problem is actually very important in terms of the computability, because maybe we are trying to solve a question with the help of computers that we cannot do that. So we're gonna waste our times. Or these questions help us to know what is the best way to approach a question. Okay, guys. So if we know that what are the capabilities, let me just circle this word. So I have the tablet, I try to use it. Okay, it's nice. No, I don't like it. Let me do it again. So these capabilities and limitations are two important features that you're gonna examine during this class. What we can do, what are limitations, what we cannot do, and what are the reasons for that. Why we are not able to solve a problem with the modern computers. Okay, guys. And there are 3 areas. These guys are like the stuff that we're gonna investigate: automata, compatibility, and complexity. The previous class in automata, in the algorithm class, we always talk about the complexity. So it's the same stuff. Okay, guys, it's gonna be the same stuff, and we are not gonna overlap anything. But the complexity is also part of these capabilities and limitations, right? So let me introduce these 3 things to you, but starting with the complexity, because like you know what complexity is. And so far, like we discussed some problems that are easy, right? If you remember from the algorithm class, there are many problems are easy, like the sorting problem. And you can say the complex study is n log n if you use like any kind of, okay, I tried, okay, it's fine. So n log n is like a well-known complex for the sorting problems, without having any kind of extra hardware. And we can say these are easy, right? And what we also know that some problems are hard. For example, scheduling problem is a hard problem. And if like scheduling such a problem, let's say you in a university, there are so many departments, so many students, so many different classes gonna be taught, and you have limited hours. Like you have all the class must be between 8 and 17, let's say, and you have limited amount of rooms, and each room has different capabilities, different number of seats. So what is the best way to schedule courses to the rooms so that there will be no conflict, right? And then all students can take all the classes, and maybe the professors have a personal restrictions, such as a professor might say that I'm not gonna be here on Thursday, so I don't have any class on Thursday. Such a restriction that can be applied to the scheduling. So what is finding the best scheduling that satisfy all the requirements are hard problems, right? Maybe you can say like the best thing is just brute forcing. Yeah, it's brute forcing, maybe like trying to, or going to like the eager approach. And you just try to fit the first class, then second one, third one, try to all possibilities. But it's gonna be hard, it's gonna take time. And complexity actually measuring which is hard and which is easy, right? And guys, my battery is gonna die. Let me just plug it in. Sorry, guys. Okay, and the complex theory actually try to answer this question: what makes some problems computationally hard and others easy? This is the question that the complexity theory try to solve, and the answer is unknown. So we don't know. We don't know why some problems are hard. When I say this hard, like n log n, we say is easy, right? Complex is easy. So there are some problems. They have, let's say, to the n complexity. For example, brute forcing it, right? Brute force is to the n complexity. So why we don't have any better approach that makes this question, this problem, has like to the n complexity, which is why we are not able to find a solution that is n log n for this particular problem, right? And then the answer is we don't know. We don't know why it's going to happen. We can just say, okay, this is a solution and we cannot do better. So we don't have an answer for why we cannot make it better. But with our current knowledge, we cannot come up with a better solution for a problem. For example, brute or knapsack, right? Let's say knapsack. Knapsack has 2 to the n complexity. Knapsack. Knapsack has 2 to the n complexity. If you remember the problem, let me just remind you. So knapsack is a problem where you have a bag and your bag has limited amount of space. And let's say the space is S. So you have items, different items. Each item has different size and different values that make it bigger, smaller. So you try to maximize, so you can put the items in your bag, right? So the idea is that if you have like n items here, n items, so what items should be put on the bag so that you maximize your value without exceeding the size S, right? Because your bag is not flexible, let's say. So this problem, the best solution that we have is knapsack. The problem is brute forcing it. We can just say include it or not. We can just try all possibilities and see that which one is better. Okay, guys. And we don't have any solution. We don't have any better solution for knapsack. Okay, guys. So this is complexity theory. And the other question the complexity theory tries to solve is which aspect of the problem is at the root of the difficulty? Root of the difficulty. Right. So why knapsack is 2 to the n? Because the best thing that we can do is just guessing it. Okay, guys. Why sorting is easy? But it's like why this is why the ORM is this way. So some problems are n log n complexity. So why we cannot make them just n or constant time or 1? What stops us to make it better? Okay, guys. So why these questions are important? Because for many real-time questions, we don't need to find the perfect solution most of the time. Don't forget that. We don't need to find a perfect solution. For example, scheduling problem, which is NP hard, which is hard problem, but we need to find a perfect solution. What if 2 classes are collapsed, two classes are conflict? How many students will affect with that? Maybe 0, because the students might not take the same courses, right? Or maybe there's only 1 student which has a conflict. So maybe you can say, okay, you can take the next class, next term, next semester. Or the perfect solution might be something like that, like all the classes has evenly distributed, Monday, Tuesday, Wednesday, all of them are evenly distributed. Maybe you find a solution in which the classes after Friday afternoon, there will be only a small amount of class will be there, which has an imbalance. So it's not perfect, but it works for you. So actually, you need to ask this question to yourself. If you want to solve a problem, do you need a perfect solution or not? Most of the time, maybe only the approximation to the perfect solution is good for you. And it might be very easy to come up with something like that. So that depends, actually. But in real life, most of the time, you don't need to find a perfect solution such as scheduling problem. But if you find only approximation, then you are good to go. You will not need to find the perfect one. For example, for knapsack, let's say you find a sequence which is, let's say, 100 of value, but the perfect score might be like 110. Either you need to spend more time on the problem to find 110, or you are good to go with 100, which is good for you. Then you don't need to spend more time on the problem, which depends on what you really want. But this is something that we need to discuss before solving a problem. What do we need? Do we need a perfect solution? Do we need a good approximate? Or like, if you have time, why not spend more time on the value or to make it perfect or not? Okay, guys, these are the concepts of complexity, and these are important because of this, to answer these two questions. And on the other hand, there are some fields, they want to have hard problems, such as cryptography, right? This is important. Some field intentionally needs to find a hard problems. Because why? Because eventually whatever you have as like the password or hashing, right? That depends on somehow a mathematical algorithms. You need to create an algorithm to solve or encrypt a stuff, right? So that it needs to be like reversing it must be really hard, right? Let me give you an example. Let's say we have a text, we have a message, let's say, and this message is encrypted with a encryption algorithm that has a key, right? Without a key, encryption not possible. And then you have a ciphertext, an encrypted text. Let's say this is your message. This is the encrypted text. So whatever happened in here is just some algorithms must be run there, right? With a key, you can lock the message, and then it must be reversible so that your intended recipient should see your message, right? By using maybe the same key or another key. It's called decryption. It's called decryption, that may be D. With decryption, you can solve the message. Also, this thing is an algorithm. There is running an algorithm that requires another key. Okay, guys. So without the key, you are not able to decrypt the message. So that you need a problem which is hard to solve. Okay, guys. So this is another approach for the complexity theory, and it just like what is the best for you? The answer is always depends on what you need. Okay, guys. Which is about the complexity, and the second topic is compatibility. And I think you heard these three guys, Gödel, Turing, and Church. These three guys are the fathers of computers, basically. The Turing and Church. I don't know what Gödel actually like contribute, but he has so many. Like these guys mostly about like the math behind the computation, but these three guys actually like has a very important role in building a computer. And these guys, basically mathematicians, they are working on computation, what we can compute, what we can solve. Okay, guys. And they guys find that like some problems we cannot solve some problems. And these are some examples: halting problem, accept nothing, accept everything. And we're going to discuss these three problems in later on. But computation is also like the main topic of this course. Because if there's a problem that we cannot solve with a computer, we should not waste our time on it. Or we should say that like this problem is unsolvable in a meaningful time. Just working on a problem, after 10 seconds, if we can't find an answer, we should say, okay, this problem is not solvable by computer. Okay, guys? We should say something like that as an output. And automata is the name of the class, guys. Automaton, like the word actually like automaton. Okay, guys, automata is like the plural form of it. Automaton is the word itself. And which means a device, a machine that can run by itself. Or you can just say a robot, more specifically. Automaton means that. And automata theory is used in many approaches, in many fields, like text processing, compilers, hardware design. Okay, guys? And this guys, the automata theory basically gives you the definition and properties of mathematical models of computation. Definition and properties. And we're going to discuss this stuff as well, because like for solving different problems, we might need a specific automata model or specific mathematical model, so that we need to use those models to solve the problems. Any question, guys, so far? If I click on Teams, I forgot how to use Teams, guys. Sorry about that. So there is no question, right? Because if there's a question, it should pop up here. Okay, then. So guys, let me give you an example. For example, you have like, I think you may heard this problem so frequently. Let's say you have elevator. Let's say you have different floors. Let's say 4 floors, 5 floors. Okay, guys, this is 5, 4, 3, 2, 1, 0. So guys, the automaton or the automaton theory tells you that, or it must run by itself, right? So this way it must run by itself. So for example, you are on the 3rd floor. Let's say you're on here, 3rd floor, and you call the elevator. You say, I push the call button. You push it, and if the elevator is on the 5th floor, the elevator takes an action, it goes 2 floors down, right? So you press a button, and when you call this button, you cannot say that go 2 floors down always, right? Because what if the elevator on the 1st floor, 0th floor? It needs to go 3 floors up, right? When you're calling it, it depends on how the machine reacts for your button call. Depends on the state of the elevator. If it is on the 5th floor, it needs to go 2 steps down, 2 floors down. If it's on like the ground floor, it needs to go 3 floors up. So that's the parameter. When you click on the same button, cause the elevator act differently. Okay, guys. So you have to model this problem precisely. You have to model this thing so that whenever you call the elevator on the 3rd floor, it always comes to 3rd floor. Okay, guys. So the model is very important here. And like if you can see this part, programming language architecture is a part of automaton as well. But guys, actually I need to say this thing. The automata or the automata theory or computational theory doesn't give you any intermediate solution because like all of this stuff is abstract. So you have a problem, let's say this is your problem, and you need a solution. Let's say this is your solution for this thing. The tools that you are currently using are not automata. You are using some tool, programming tool maybe, or any kind of, I don't know, whatever you need to solve this problem. In the programming language like Python, Java, it doesn't matter, whatever you use here. You just see this part because this is what you see as a practice in real life. But behind this thing, you see compilers here, right? Behind this thing, there is automata here. There are algorithms, the PL, programming language, the stuff that you learn in programming language, like lexical analysis, static analysis, syntax analysis, right? Everything is behind this thing. They are just, you're not able to see that because they're abstraction. For example, when you write a program in Java, it uses automata, finite automaton, to understand what you write there. Because compilers need automata. If you have any kind of artificial intelligence, let's say you build a program that plays chess, you use context-free grammars. If you know that, maybe you know it, maybe you don't know it, but your tool gets benefit of context-free grammars to play chess. Okay, guys. So that's why, like I say, my students this thing, like being on this part is not computer engineering. Being on this part is just developers. Anybody can learn how to use this tool is a developer. But what you separate from developer tool, what makes you engineer is knowing what goes on behind the scene, right? So that's why algorithm class and automata class are like the most important class for me, like in terms of the engineering. So actually, I drew this table last year during the algorithm class, but one like the really like fundamental things is there are 2 classes, which is algorithms and automata class, they are there. And these are like the step one. These are very fundamental stuff that you must know. Okay, guys? Then on one layer up, you can put PL, object-oriented programming. What else you have? Data structures. On top of it, you can add the other stuff, like other core courses like database, signal, whatever you have with us, operating systems, and maybe software engineering, right? These are just like any kind of programming, like object-oriented programming, it's important. And then you have the elective courses, electives. But these two guys are your fundamental stuff. This is like knowing the complexity of the problem, like doing the analysis of the program or your problems is really important. What makes you an engineer? So maybe currently in your lab, you're gonna just build some program with Java or JavaScript, you can make a good money, but this is not being an engineer, right? This is just being a developer. But doing analysis, or my professor from Top University, Oğuz Ergin, maybe you know him. He did his internship in Intel in Spain, and he was assigned a job where he needs to build a microchip that use like 10% less energy. The microchip should do the same thing. Everything must be the same, but the new design must use 10% less energy. So you don't know why they need it, but without knowing all of these details, right? Why do you need like 10%? How can you cut the program which must do the exactly same stuff? The same time, same resources, but the 10% less energy you need to consume. So that doing this kind of analysis requires to know these two stuff incredibly well. Okay, guys. So algorithm, you should pass this one. I think you don't have to, right? This is not a prerequisite. But I think you need to pass discrete math. Without discrete math, you cannot take this course. But as I said, like these two, I think I can put discrete math here as well. Discrete math. These three courses are extremely important for you guys, let's say. Okay, guys. Any question? I think there's no question. We can keep going. So in the book, it starts with a like chapter introduction, and it just use the space for reminding you some mathematical notions and terminology, like what is set, what is sequence, what is the Venn diagram, something like that. Also, we talk about the graph, some proofs. I think, like, you know what set is, right? I'm gonna just do very quick review for that, and then we pass. So that set is basically a group of objects, and the important part is like the order of the set does not matter, or if it has repetition, they are not important for you. Order doesn't important, repetition doesn't important. So if you see something like set is 5, 20, 22, as you can see, which is equal to 20, 22, 5, and 20. These two sets is identical. Okay, guys? Because order doesn't important, repetition doesn't important, you can just ignore this thing. Order doesn't make sense, order doesn't important for you. So that you can say that these two sets are identical. Okay, guys? And for set, we use this curly braces to show that this is a set. And for sequence, we use just parentheses. We're gonna see that. This icon is 0 for element of it, so 5 is element of this set, but let's say 7 is not element of this set, so you need to use this icon or symbol. So this is subset. If all of elements of A is also element of B, we consider A is a subset of B, right? And also we have some kind of predefined sets such as natural numbers, right? What are the integers, right? Natural numbers were 1, 2, 3, 4, it goes on. If you have a sequence, like if you have some kind of, it goes for infinity, you can use 3 points after you give a sense of how the sequence is going on. Right, guys, you can use three dots to show. For example, you can say that next element is going to be 4, 5, 6, 7, it goes on. For the integers, you can say this is 0 and -1, 0, 1. So you can say it's going to be 2, it's going to be -2. You can say that. So you can use these 3 points. So this is for empty set. If the set has no element, we use this symbol for it. Also, you can define sets with these rules, right? Which means that your set contains n squares where n is element of n. So basically your set is the numbers of that are full square, right? Like 1, 4, 9, 16. It goes on. There is no 0 in n, right? So you can define rules something like that. Or you can say that, for example, n, where n is equal to 2m, where m is element of n, let's say. So if you have such a rule, which means that this is for the even numbers, right? Your n must be 2m, where m is element of n. So you can just define a rule for your set as well. So this is for union, this is for intersection. We're going to talk about them in Venn diagrams. So this is a way of showing sets actually, another way of showing that thing. You just draw a circle to limit the coverage of your set. For example, start T is the name of our set, which contains the word starting with letter T. So we can show it like this. Or like this, and Z, words that end with the Z, right? Venn diagrams. And the overlapping areas of those Venn diagrams show that these are intersections. It has the common elements. For start T and Z, topaz must be here. And Z start J, jazz must be here, right? On the overlapping area. This is Venn diagrams. I think you know that stuff. I just want to show you that. And sequence is another notion. Text and sequence are like two fundamental stuff on the math. And sequence, a list of objects in some order. The difference between set and sequence must have order. Order matters in sequences. And repetition matters as well, as far as I remember. The repetition matters. So for example, 5, 20, 22 and 25, 22, these two sets are not identical. They are different. These two sequences are two different sequences. They are not identical. Okay, guys? As you can see, like the order is different, so that they are showing different sets, sequences. If a sequence is finite, it's also called a tuple. If a sequence has 3 elements, it's called 3-tuple. Okay, guys? If it has a 2 element, it's called pair. It's a specific name. If it has 2 elements on a sequence, it's called pair. But this is a Cartesian product or cross product, as far as I remember. A cross product B gives you this, like the first element, all of the first element from A, and then the second element coming from the B. Okay, guys. Functions, another topic. And as a function, we have this formula. But for the function, do you have any question? Let me see Teams. I think there is no question. So guys, for functional relations, we have this formula f a and b. This is the notion that we show the functions, and functions are some kind of mapping. So functions maps items from domain to the range. So you can just demonstrate this thing like this. Let me draw this here. So this is your domain, this is your range, this is D, this is R, and whatever you do is you have item here and you map it on the range part. Okay, guys. So for example, in here we said that minus yeah, minus x must be x, right? Okay, minus negative x is gonna be the x, right? So if you have minus 1 here, it goes be 1 here. If you have 2 here, it goes minus 2 here. Right? This kind of mapping here. It gives you 0. So do you have this thing? No. So if you have item, how can I say that? If all the elements in the range is mapped with the element from the domain, if there's no element left on the range, it's called onto. The function is called onto. I think in Turkish it's called örten. I'm not sure about this, but it's called onto. Okay, guys? And it's called onto. Because that you have one element here on the domain that has map for each item. So there's no items left here on the range. Okay, guys? Example is, if you say something like that, for example, absolute value, right? Absolute value is from Z to N, let's say. And union, let's say 0, at 0 as well. So this is an onto function, right? Because absolute value, if number is negative, you make it positive, and the same value, like negative 5, absolute of negative 5 is equal to 5, right? Absolute of 5 is equal to 5 as well. So your domain is bigger than your range, but you can fill all the elements on the range. There's a map, there's a function that has a value for each value from the range. It's called onto function. Okay, guys? So this is also called relation. These are famous like rock, scissors, and paper. So it's called Beaks relation. The type of function, but it takes 2 elements and it gives you true or false. Now, scissors false, scissors is false. No, scissors doesn't beat scissors. Paper beats rock is correct. Rock beats paper, false. You can find relation. But it's another way to show a function or a relation. Okay, guys, you can prepare a table and show the result. And we have these are the features of the function and relation. So if you have x, for each of x, if you have x are x, which means that fx is equal to x. It's called reflected. If your fx equal to y, so we show it like x r y, in short, for short. The x relation y implies that y relation x, that's called symmetric. Okay, guys? And transitive means that if your x is equal to y, fx, and fy equal to z, which means that fx equal to fz. This is transitive. 3 main features for the function, and it's going to be useful in later on. Not right now, but later on we're going to use those stuff. So we're all out of time. I think you know what graphs are. Okay, these 2 stuff are important. I need to talk about this stuff. I think you know what graphs is, or you can just study for that thing. So strings and languages are important, guys. So then, let me see. Boolean logic, proof. Okay. I think the proofs also important. Okay, next time we're going to start from the proofs. So let me explain strings and languages because these are, so we talk about the formal languages, right? So this must be important. So guys, alphabet is non-empty finite set. We use the alphabet to create words or strings. Okay, guys. And the member of the alphabet are the symbols. Okay, guys. Alphabet, we use symbols as alphabet. For example, 0 and 1, that creates an alphabet. Or A to Z, all lowercase letter, that creates an alphabet. Or just you can just make a mixture. 0, 1, X, Y, Z. It's an alphabet. In alphabet, we have symbols. We use the symbols to create strings. Okay, guys? And then the string is just a the finite sequence of these symbols from the alphabet. For example, if your alphabet has 0 and 1, this word 0, 1, 0, 0, 1 is a string over your lambda 1, sigma 1, sorry, right? And this icon shows the length of your string. And you can concatenate two strings, Z, if Z is ha ha ha, and WZ is 0, 1, 0, 1, ha ha ha, right? Just put them next to each other. They don't need to be on the same alphabet or language, but you can just do the concatenation over time. Okay, guys? So where's the language? I don't have the final definition of language. So guys, and the language is, definition of language is the set of strings that you can create with your alphabet. Don't forget that. Set of strings that you can create with your alphabet. But you have to satisfy rules for that. For language, you have rules, and by using the alphabet, you can generate strings, set of strings that obey the rule, let's say. I think we're going to talk about it later on. Please look at this Boolean logic, and then definition, theorem, and proofs. Okay, guys, I think we need to stop it here. So these guys, I think you know this stuff. Like this is just like the proof by construction, proof by introduction, and proof by contradiction. Three type of proof of induction, contradiction, and construction. Three type of proofs that we have. So you don't have any assignment, but if you want to solve this exam, like as I said, if you give me your solution, I give you the feedback. It is not mandatory, but if you give your solution by next class, I can give you the feedback. Okay, guys? Please read the other parts. Like the definition of them is not like hard stuff. You just need to read them, and you'll be good to go. Any question, guys? Okay, then. See you next week. So I'm going to do my office hours right now. If you have questions, you can ask me. Come see me, or you can just send me email. Then we can just discuss. Okay, guys? And then if there's no questions, see you next week.